Alright, let's get started. So, the first thing I want to do is go over homework 1 solution briefly. So the area, I don't know why it's doing that. Okay. Alright, so there's a text box on the class homepage where you can type password to gain access to see the homework solution. And the password is the same as the password you use to log into the database server. Okay? And okay, so here are the solution for homework 1, and in particular, I break the solution into 2 parts. The PDF file has the solution for problem 1 and 2. Then I have a SQL file that contains all the SQL queries for problem number 3. So the first problem, relational algebra and triple relational calculus, they are fairly, once you understand the logic behind the construction of a particular query, right? Whether you do it in relational algebra or triple relational calculus, actually it's not that hard, right? So I will go over the relational algebra really quick. Then triple relational calculus can refer to my solution. Okay. The first one, trivial, is just a division. Okay, so I will skip that. Second one, it's a little bit trickier to solve because in relational algebra you do not have this notion of aggregation. You do not have the notion of aggregation. So you cannot. Yes.
In the first one, I know it's really simple, but you're dividing by film IDs from the inventory table, and so, but it says all films. So if we did film IDs,
yeah, if you join with the film, yes. So in the I understand what you're saying. So in the extreme case, you can argue maybe there are 1 or 2 films in the film table, but we have no inventory for it. So when I say rent all films, do you mean rent all film from the inventory, or do you mean rent all films that are all there? Either one is fine.
Okay.
Yeah. Now, number 2, you do not have aggregation operators, so you cannot count how many staff working for a particular store. But let me pull out the schema. So by the way, you need to turn in your homework at the beginning of the lecture. Once I start going over solution, I will refuse, obviously, for obvious reasons, to take any submissions. Okay. If you look at the schema here, so you have a store, you have staff. So I didn't cover ER in this class, but some of you have taken ER from the undergrad class. If you understand a little bit ER, you know there's a one-to-many constraint between store and staff. Meaning one store may have multiple staff members, but a staff can only work for one store. The reason I can tell that is because a store ID is actually placed into the staff table. You can do that if and only if there is a one-to-many mapping between store and staff. Otherwise, suppose if it's a many-to-many mapping, meaning a staff may potentially work for multiple stores, then you cannot possibly have store ID as part of the staff schema, because you simply don't know how many store IDs you should have included for a particular staff member. That's not a constant, right? One staff may work for 2, the other staff may work for 10. Then how do you decide whether I should have 2 store IDs or 10 store IDs in the staff schema? In that case, what you should do is just create a separate table to capture this many-to-many mapping. But those are details from algebra data class. I will not go into further details. That being said, it is possible that a store has multiple staff, and the right way of doing this in SQL is easy. You do a group by, you count, right? But how do you do this in relational algebra? Well, the trick is to do a self-join. I actually answered one of the students' question in Canvas discussion forum. I said you can use a self-join like what I'm doing here. So first of all, you use the renaming operator to rename staff table twice. Basically what you're doing is to get 2 copies of the staff instance. And you refer them as staff 1, staff 2. And you rename the corresponding attributes as well. Staff table has many attributes, but as far as this problem is concerned, you only need to worry about staff ID and store ID. You don't need to worry about anything else. So you rename them, then you do a join where you enforce the condition that store ID must be the same, but staff ID is not the same. What do you get? Well, only those stores who have more than 1 staff will actually participate in this join. Those stores with 0 staff or only 1 staff will never satisfy this join condition. Then you put out the store ID. Those are the store IDs who have more than 1 staff members. How many staff members they have, I don't know, but I know for sure they have more than 1 staff members. Then I use all the store IDs minus with those stores who have only 1 staff member, then I get stores with only 1 staff member. Okay? So that's this. The rest, problem 3 is easy, I will skip. Problem 4, yeah, question over there.
So pretty much all the joins with this schema, you really have to use data joins because there's a last updated field on pretty much every table.
You mean, can you use natural join? Is that your question?
Well, I mean, because they both have the last update field, so join on that probably, right?
You join on which field? Can you be more specific?
Like for inventory and rental, for example, they both have a last update field.
Which problem you're talking about? First one or?
Yeah, like the first one.
Okay. So let's look at the inventory, huh?
So they have, so inventory has a last update and rental has a last update.
Yes?
So you couldn't natural join on them.
No, you cannot natural join on them. The update on them are, update in database are not atomic operation. So the last update value will be different for.
Yeah, so just so like on the.
If you do a natural join between the two, let's say inventory and rental, right?
Yeah.
The common attribute obviously is inventory ID, right?
And last update.
Well, no, last update is a special attribute. It's not part of schema. I explained it. It's defined by the trigger. I explained in last lecture, right? It's part of your trigger definition. It's not.
So it doesn't count as part of.
Doesn't count. No.
Oh, okay.
Okay. It's not part of your schema.
So the last update is not an actual column. It's just.
It is actual column, but it's not part of your schema definition. It's just a database defined column to capture when the timestamp of last inserted tuple. That makes sense?
In my SQL queries, I used natural join on all of them first, and it didn't work because of the last update, because I had to change it.
Well, the database might it depends on the particular data system implementation, but schema-wise, if you look at the schema-wise, the schema definitely, even though all this table has the last update column, but it's not part of your, let me say, meaningful schema definition.
Right.
So you should not count that as part of your natural join operation. Okay. Now, problem 3D, they escape problem 4. But when the all and only those films acted by Emily D. This part has two parts, right? First of all, you have to print all films acted by this actor. That's just a division. That's simple, right? This is the first part. Okay? That's the first part. That should be fairly straightforward. Some of you might be confused by how do I find only those films acted by Emily D. Because you could have rented all films acted by this actor, but not necessarily you have only rented those, because you may rent additional. The other way is also true, meaning you might have rented only those films acted by this actor, but not necessarily all of the films acted by this actor. You follow me? So what you want to do is, you find the set. Those are the people who have rented all films by Emily D. That's essentially this first part over here. Then you find those sets. You find those who have rented a film not acted by Emily D. Rent at least one film not by this actor X. Then what you want is this part. That's essentially the idea here. And how do you find a film who has rented a film not by Emily D? That's trivial. Just a join between rent and the films not acted by Emily D, which is F2 right there. How do you define F2? F1 is the film acted by Emily D. Use all film subtitle way. Film by Emily D. Those are films not by Emily D. If you survive this join, meaning you have rented, I don't really care how many times you have rented a film not by Emily D, but you have rented at least one film not acted by Emily D. Okay, so that's that. Tuple rule calculus is same logic, let me go to the SQL query. Okay. So these are the SQL queries. Of course, keep in mind there might be multiple ways of doing these SQL queries, but nonetheless, your solution should be somewhat similar to what I have here. Okay. There's some flexibility, but not a whole lot. Which one I should go over? I will go over just one, then the rest I will let you guys to figure out. Seems like which one you guys wanna, which one is you feel most challenging I need to discuss?
Number one is difficult at that.
Number one is difficult? Number one is just division, right? No? Number one is just division.
Emily D is
Huh?
food. Emily D is hard.
Emily D is hard. Okay, I will go this one. Number one is just division, right? If you feel number one is hard, you should spend a little bit more time in reviewing that exercise. Okay. So let me go over number 4. Let's see the question first. Or it was find the customer ID who have rented. Oh, okay. Same as relation algebra, right? So that being said, the SQL query follow the same logic as what I have done for relation algebra. There's the division part, there's the join, then subtract. Okay, so it's the same logic. Looks complicated, but essentially this part up to here is that division. Looks complicated, but it's just the division. Logic-wise, this is extremely simple. Just the division, as we have covered several times in class. Okay? And this part is that second join, which is whoever has rented the film not by MAB, then you accept. So that's part 4. Okay? So given that, I'm willing to take one more challenge. Which one you want to go over? Huh? Which one you find is kind of hard to do?
Can you look at your second one? Just
Huh?
Can we look at the second one just really quick? Your
Second
solution.
one, print the store ID and address for each store that has only one staff member.
Oh, can we go back to your solution though? For number 2?
Number 2, here, because we're in SQL, we have aggregation, we have group by, so you can still use the logic of self-join as we did for relation algebra, but you don't have to. In SQL, you can just do group by and count. Yes? Any?
Are you going to post this file first?
Yeah, of course, it's posted.
Okay.
Let me update, there's a typo in my post. Okay, so if you want to look at the output, this is the output. The first one is no answer. There are no customer rent all films. There are 2 stores, has only one staff ID. 3 and 4 are no answer as well. I forgot what's 3 and what's 3. 3 is all and those only by only, that's 4. Actually, in this database, there are no customer and staff live in the same city. Right? So the output is now. Number 5 is largest inventory is this particular store, MySQL Boulevard. Okay? And who has acted the least number of films, that's MLD. That's the reason why I asked you to say whether who have rented all films by MLD. Because that has the highest probability, right? He or she has acted the least number of times.
Although she's in a low number of films, she might not be very popular, so they don't want to.
That's right, yeah. And then the city name, total amount payments by the city, total number of customers in that city, and top 15, so that's the answer.
For your 7, are you missing a distinct? Because shouldn't it be for
7 or?
yeah? Because
The customer count needs to be distinct.
yeah.
Let me
Otherwise,
see.
you count.
Maybe I made a mistake there, let me see. You mean this one, right? So, let me see. So look at my solution, some amount, so that's the total amount by the city, and where, ST, sum and count, group by customer ID, city ID. No, I don't think you need to do this. Why do you need to do
For
this?
the count star, like
Your
count
group
the-
by the customer ID, right?
Yeah, but you could have a. Is it for customer?
Oh, I see.
Yeah.
Yes. Let me think about this. Some amount, customer address ID, Steve.
There's only like, in most of them, there's only like one customer from those cities. But they have multiple payments, so that if you don't do this.
I see, yes, you have to do this thing, because, yes, okay. All right, so I will fix that. Okay, that's the homework one. Any questions so far? I will move on to my lecture, yes.
I ended up using the with keyword, is that okay?
What do you mean with keyword?
So you can, it's kind of like a view where you define a table with this, like you define the table, and then you have a select statement, and then you can use that for the rest.
So basically you define a temporary table, is that what you're saying?
Yeah. Is that,
Well, yes, it's fine, but
Okay.
it's what you have done essentially is same as using the as keyword, right?
I think so.
Yeah. Okay. So let's move on to the lecture. Let me remind you guys. Many of you may have database experience before, but you probably just use database for like really simple applications. Right? This class will be significantly challenging than what you probably initially thought. Homework 1 is probably the easiest homework you will ever have in this class. And project, okay? We're gonna start working on project like today. I will release project 1 later today. I will go over project 1 briefly later today, but let me show you the system you're gonna build, the documentation for that system. I posted. This is all the classes, okay? So you're gonna build the system over this. So this requires significant coding skills and teamwork. When I say you work in a team, you really need to work in a team. Okay, it's not like you code this function, I code this function. That will not work, most likely. Okay, so you definitely need to. I don't know when. Have we passed the deadline? Maybe I should mention this too early. Have we passed the deadline to withdraw? Okay, all right. Okay, it's safe for me to mention this. No turning back. So we're in this together. It's like in roller coaster, right? You realize, can I get off? No, too late. Okay. All right. But I think we'll be fine. Right? You will learn all the things. Okay. All right. So let me continue on the lecture.
It's actually not related. Just saying.
Okay. All right.
It's really good draw. Just didn't want to repeat of last lecture.
All right. So we talk about storage engine, buffer files, and disk. We talk about this is where we stopped. Yeah, right here. So we talk about the difference between sequential rate and random rate, right? Sequential access and random access. And if you look at this graph here, oh, by the way, one more thing, I received an email because this class consists of two groups of students. The first group is those typical normal CS students mostly, and maybe a few other students from other departments. But the first group consists of full-time students at the University of Utah. The second group, I think we have a few of big data certificate students. And for the second group, sometimes it's really hard to come to lecture, physically come to lecture, because typically students from the second group are working professionals. So in my class, I always require you to submit physical print-out copies, physical copies of your homework. But for the second group of students, I'm willing to make an exception. If you are unable to make it to a class due to conflict of your schedule because you're working, you can make the electronic submission to the TH, but only to the second group of students. For the first group, as long as you are here, you are a student, I don't care whether you come to lecture or not in typical classes, but whenever a homework due, you need to come and just turn in your homework, a physical copy. You can leave as soon as you turn in this, that's fine, okay?
Could we turn it in like one or two
Before?
lectures early? Or?
Yeah, but then I would recommend just hold on to it and turning when it's due, because I'm worried that it will be misplaced if you turn it ahead of time. That makes sense. The reason we do not accept electronic submission is once I do allow that, many of you start sending electronic submission. That create a lot of actual burden for the TAs to print and to make sure your homework is not misplaced and so on and so forth, right? So to be fair, I simply say no electronic submission to all. But then for the big data certificate student, I'm willing to make exception. Okay. All right. So
So would it be email or Canvas?
their email is posted on the website.
To you or all the TAs?
To the TA. To the TA.
Okay,
Their emails are.
right, yeah, I saw it. Thanks.
Okay. By the way, the other thing, speaking of TA, I made an announcement. One of our original TA, Zhao, has a medical condition that will take him a while to recover. In light of that, we decided to switch him out of the TA role, so that he can concentrate on his recovery and for this semester. So what I did is I add a new TA, Guidong, who is also my PT student. So he will be substituting Zhao. And good news is he has no conflict to the original TA hours that Zhao has posted. So you will use the same TA office hours to see Guidong. Okay? So we talked about sequential access and random access. This is what it looks like for sequential access. As you can tell, clearly the overall kind of somewhat a linear curve. The reason is you are sequentially reading the next block or next page from disk. I explained what I mean by next. In hard drive, is basically next refers to the next page from the same track. When you run out of all pages from one track, you go to the next page from the same cylinder, which is the next track on the same cylinder. When you run out of all pages from the cylinder, you go to the next page from the first track of the next cylinder. And the cost, if you think about when you do sequential access, is basically one movement of your arm to make sure the head of the arm is aligned with the track that holds the first page you want to read. Okay? Then there is a rotation delay, which is even if you're aligned with the track you want to read, the first sector from the page you're trying to read might not be right under the head of the arm yet. So you need to wait for that to be rotated over to be right under the head of the arm to start reading data from disk. Okay? So if you think about it, there are two delays involved in reading data from disk, which is the movement delay and the rotation delay. Let's talk about the second part, the rotation delay. The rotation delay obviously depends on two factors. One is how fast the disk can rotate. Second thing, what's the relative position between the first sector of the page you try to read and the head of your arm. Right? Those determine the rotation delay. And the relative positions of these two guys, meaning the head of the arm and the first sector you try to read, these obviously are variables. It varies case by case. Each time you try to read data, this is different. So it's kind of hard to quantify this precisely, so we use an average case analysis approach. We analyze what's the average case for you to wait for the first sector to be rotated right under the head of your arm. And what's the average case? Well, the average case obviously is to wait for half rotation. It's a circle, right? So if you consider all possible cases, averaging out is half rotation. So rotation delay is calculated by using this average approach, which is essentially time to rotate the disk for 180 degrees to do half rotation. And how you calculate that is by looking at the parameters of the disk. For example, if somebody tells you, somebody tell you that this is 7,200 RPM. RPM stands for rotation per minute. Okay, what will be the rotation delay? What will be the rotation delay per our discussion? Well, half of that is 4.16 milliseconds. You follow me? So that will be the rotation delay. The 6-time delay quantifies the time it takes to move the arm in and out, to align the head of arm to be over a particular track you try to read data from. Again, this is a variable, right? Depends on the beginning, at the beginning of your read process, what's the location of the arm of the head of the arm, and where is the track you try to read data from. Okay, so it is a variable. However, you know, to do analysis, we simplify this this whole thing quite a bit. We argue that, you know, that this surface, the radius is a small value. This surface, actually, if you ever open a hard drive, the platter is kind of like this big. It's very small. The radius is very small. This movement in and out is fairly fast. So we just use the average value to quantify that as well. And typically that value comes from this manufacturer. They will tell you what that value is. That name, they give a name for that. That's what they call the 6-time. So next time when you buy disk, when you see something called 6-time, you understand what it is. It is essentially moving arm in and out. What's the average time to do that? Okay, so that's the 6-time delay. So now, with this being said, what's the cost to do a sequential read of a number of pages? What's the cost to do a sequential read of, let's say, 100 pages? I want to sequentially read 100 pages. What's the cost of that? Well, you need to pay a 6-time delay, which is, for example, 8.5 milliseconds. Then what you have to pay? You have to pay a rotation delay, which is half rotation. For this disk, that's 4.16 milliseconds. So you are about 12.6 milliseconds. You've spent this much time already. But this time is to be ready to read the first page. Now you're ready to read the first page. You follow me? But then your goal is to read 100 pages, right? What's the cost of that? Well, there are two things involved. One is, in order to read 100 pages, a bottom line you have to do, a bottom line cost you have to pay is to wait for those 100 pages to be rotating over the head of the arm. So you have to rotate those 100 pages over. So there's a cost for that. And how do you calculate that? Well, you use the rotation time, 7,200 rotation per minute. You calculate how long it takes to do one rotation, which is 8.3 milliseconds. Then you look at the hard drive configuration, how many pages in a particular track. Let's say if I have 100 pages in a track, then rotating 100 pages takes exactly 8.3 milliseconds. Let's say I have 200 pages in a track, then rotating that 100 pages takes how much time? Well, half of that, 4 milliseconds. So with that number, you can calculate how long it takes to rotate 100 pages, or how long to rotate 1,000 pages, 10,000 pages, and so on and so forth. Of course, there is a catch though, which is if you're reading a lot of pages, let's say 10,000 pages, which happens when you try to do sequential read of large file. You follow me? When you finish reading all pages from one track, you move to the next track from the same cylinder. This doesn't cause you any delay because you have multiple arms. They all are at the same location, so you can immediately start reading the next page from that track. Maybe you have to pay a small rotation delay, but typically we ignore that. But problem arises when you have finished reading all pages from the same cylinder. Now you cannot stay still to read the next page. What you have to do is move the arm either in or out, depending on, you define next as the next cylinder from a bigger circle or smaller circle, right? Depending on how you start this thing. So you have to pay a 6 time delay every so often. Every calendar you have exhausted. So for every calendar you have exhausted, you have to pay a 6 time delay. So in your calculation of how long it takes to read X number of pages, you need to take that into consideration. So suppose X is 10,000 and each cylinder has 1,000 pages. Okay? Then you have to pay 10 6 time delays.
Do you not have to pay more rotational delays?
You do. I mean, whenever you move the arm to a different cylinder, you cannot start reading right away. You have to wait for quote unquote the next page. But you know, we kind of argue for the ideal case where when you move the arm out to the next cylinder, the next page is right there, you can start reading right away. Because if you go to read everything, it doesn't matter, you know, what's the next page to read. You just start reading anywhere from that track right away, right? Does that make sense? So typically we only quantify that 6 time delay.
Because it's sequential, right?
Only because it's sequential, yes. Okay, so that's the cost for doing sequential read. One more subtle, really subtle point I'd like to make is there's another cost, which is when you convert data from magnetic field to something that the memory understands, meaning to positive and negative charge electron particles, that conversion takes time too, obviously. Right? Convert from magnetic north field to negative charge signals, that will take time too. You follow me? Meaning when your arm is aligned with the page you are reading and the page is doing rotation at the same time, there is a cost of converting data as well. You follow me? That's what we call the transfer time. Okay, that's what we call the transfer time. Okay, so transfer time contains 2 parts. One is the time to do the rotation itself, which I have explained. When you try to transfer one page of data, you have to wait for that page to rotate over the head of the arm. So transfer time has 2 parts. One is the physical rotation time, and the second part will be the time that takes to convert from magnetic field to electrical signals. However, typically, the physical rotation time dominates that conversion time. The conversion time is actually fairly small compared to the physical rotation time. So in most scenarios, unless I otherwise specified, as far as this class is concerned, whenever we say transfer time, we only care about the first component of that transfer time. We typically ignore the second component of transfer time, which is the conversion time. You follow me? So far so good? Okay, fantastic. Now, once we understand sequential access, let's look at random access. This is what happens when I run a sequential workload together with a random workload. You can still observe that sequential workload, but random workload starts to kick in. Yes?
Just one question. I'm trying to remember, if you have 2 tracks that are different diameter, are there a greater number of pages in the larger diameter?
Yes. Good question. Good question. The answer will be yes, but however, the difference is not significant, so we consider it's a constant number. Okay? But very good question. Excellent. Okay? Now, this is what happens when you run one sequential workload with one random workload. You can still kind of observe that sequential workload because what happened to the disk driver is this driver will do a non-robbing service between the two. If you only have one random workload, it comes back to that sequential workload fairly quickly. You can still kind of observe that sequential workload. But if you keep adding random workload to it, eventually that sequential workload gets destroyed. You cannot observe anything out of this. So and if you look at the throughput, megabytes per second, which is the total amount of data you can get out of your disk per second. No matter how many workloads you're running, I don't care. I'm running 10 or 20 workloads. I do an aggregate count of the total number of bytes I can get out of my disk from all these workloads I'm running concurrently. Right? That's what this experiment is about. as you can tell, not surprisingly, the sequential workload give you the highest throughput. That's the first experiment you typically should run when you get a new hard drive. Typically, you don't run this, but I usually do this, right? Whenever I get a hard drive, I run a sequential workload for 30 minutes, then measure my throughput. Because that tells you the best case scenario you can get out of your disk. That's the best case scenario. You cannot beat this. You cannot possibly beat this. Cannot be faster than this. You follow me? And this also tells you a lot of other interesting things. If you're doing parallel computation using a cluster of stations, workstations, this tells you also what kind of switch you should buy. You follow me? You network switch, the bandwidth must be at least higher than this number. Otherwise, you suffer loss when you do node-to-node communication, potentially, right? If you do sequential read and sequential write. So this value is kind of interesting, right? But once you start adding random workload to it, not surprisingly, the throughput drops. With one random workload, it drops just a little bit, like maybe 10 megabytes per second difference. But as you keep adding more and more random workloads, the difference becomes staggering. Right? The difference becomes, it drops from almost 70, 80 megabytes to just about 10 megabytes per second. Just about 10 megabytes per second. And this is the typical kind of throughput you get from your disk, because your operating system over time plays files in different locations, and most time you are doing random rates. That's why it's a good idea from time to time in Windows you do what they call the disk segmentation. That's essentially try to move blocks from the same file to be consecutive on disk, so that you no longer pay random access when you access that file, rather you pay sequential access. So that's essentially what they're doing. Disk defragmentation, that's the word. That's the terminology you use, okay? Alright, so lastly, do I have, I thought I have a few slides on SSD. Do I have SSD somewhere? Okay, I remember I added a slide for SSD, but somehow it's not here. So I would just use the chalkboard to explain what the difference between hard drive and SSD. So many of you laptops, including mine, come with SSD nowadays if you're willing to pay some additional price, right? So what's the difference between SSD and hard drive, and why it's a good idea to pay the actual price? So a major difference between SSD and hard drive, now after we cover, by the way, what's the cost for doing random access? Which is 1 seek time delay, 1 rotation delay, and the time to rotate one page. But the difference, the key difference is for sequential access, what you do is 1 seek plus 1 rotation delay plus the rotation time for X pages. And this you can calculate, right? This you can calculate. But the critical observation is you pay this part only once. But for our earlier argument, you may have to pay this part, especially the seek time delay, every so often, depending on how many pages you can hold in a cylinder. So there's something going on here, right? You need to be careful in your calculation, right? But the rough estimate is this. What about random access? Well, it will be 1 seek plus 1 rotation delay plus rotation time for one page, because each time you read just one page, and x times this. And this obviously will be much more expensive than this. You follow me? Once you understand this formula, it should be fairly easy for you to understand the difference between SSD and the hard drive. So SSD, when it comes to SSD, by the way, for hard drive, it makes no difference between read and write. Either you're reading or writing data, this is kind of the cost you pay. But for SSD, there's a significant difference between read and write. So for read, very simple. You can think about this kind of like RAM, random access memory. I talked about what's RAM, right? The only difference is the unit cost is slightly higher compared to a memory setting, but for the rest part, it just behaves like a RAM. Meaning, random access cost is a uniform value no matter where you read data from. So you no longer observe this difference here. It's just like a RAM. You follow me? The only difference between SSD and main memory is that unit cost for reading one unit of data is higher for SSD, slightly higher. Okay? That's why SSD is much better than hard drive for that reading. Okay? Furthermore, the cost of reading one page of data, from SSD is much smaller than reading one page of data from disk, slightly bigger than reading one page of data from main memory. Other than that, it behaves like a RAM. Okay? So that's for the read part. For write, this is interesting. Okay, write, you have to distinguish two types of writes. I will call them, I don't know what's the right word to use, but let's say clean write and update. So clean write means that you're writing data first time to a particular block. A block in SSD, by the way, a block in SSD here refers to a particular concept in SSD. A block is a collection of pages in SSD. Okay, typically the block size is, depending on the SSD configuration, right? Most block size is maybe, let's say, 256 kilobytes. So that's what I mean by a block. So SSD is organized into blocks like this. Initially, they are just what we call the clean and write blocks. There's nothing there. If it's a clean and write block you try to write data to, that's very fast. That's almost as fast as reading data from SSD. So you can write really fast. But whenever you try to do update, meaning the block currently is holding some data, and you try to write value over, this is when SSD becomes fairly expensive. The update process in SSD is as follows. So suppose I want to write to this block. Suppose I have some block X that I have this piece of data I want to write over this region. From here to here, I want to write over. Okay? If it's a disk, you can just go and write over. You pay 6 times delay, you pay rotation delay, you can start writing over data on that region, right? For SSD, unfortunately, you cannot do that. For SSD, what you have to do is, first of all, copy this block X to a particular block from eraser block. So there is a particular block, a few of them reserved to do this erase operation. You follow me? So what it does, it will copy this over to this erase block. In that process, I will read the data out of it to main memory. So I will read the data to a main memory block, to RAM. And then write this over to that main memory copy of this block. So that main memory copy now has the intended value for this block. Because I copied the original data, then I write over to the correct location. So this now has the correct copies of data. And then this block, once it comes to the eraser block, will be erased. So it becomes, one more time, become a clean block. Then I can write this whole block to that clean block. So that's the update operation in SSD. Do you follow me? Obviously, this is expensive. Expensive, let me finish, then I'll answer your question. Expensive in two senses. One is take more time than just simply write over. And secondly, what's the second cost? The second cost is if you write to SSD too often, if you especially do updates all the time. If you just write clean block, that's okay, because just one time write, then that's okay. For example, you create a new file on your SSD drive, that's okay. But if you keep updating data on your existing file, and you keep doing this erase operation, the life expectation of your SSD drive will reduce dramatically. Meaning, initially you might use your SSD drive for 2 or 3 years, but if you keep doing this update operation all the time, writing data over and over, you might need to replace your drive like in a year, in less than a year, or something like that. Okay, so it reduces the lifetime of your SSD drive.
I was just going to ask, so does it copy it to the erasure block as kind of like a backup in case it fails?
No, it's not kind of like a backup. It's because the particular physics that go into the construction of SSD, they have to do this in order to do update. It's not really just for the purpose of backup. Data is not actually backup. Data is copied to the erase block, erased, right over, then placed back. So it's not for backup purpose. It's the particular physics that people leverage to build this SSD drive leads to this particular type of operation for us. Okay? Now, so that's SSD. As you can tell, obviously there are some optimization here you can do, right? If you have a main memory and you have hard drive and SSD, when they form a hierarchical system, you can be smart about when to do writes to SSD, when to do write to hard drive, when to do buffer your data, and so on and so forth. So there are tons of research going into this space. Okay. Finally, before I move on to the next part of our lecture, I want to highlight that there are some new development in this space, which is not available yet, but we expect them to be available in maybe next year or the year next year, in 2017 or maybe 2018, which is called NVRAM. We know RAM, right? RAM is random access memory, which is the model I explained last lecture. This guys are RAM, right? But theoretical model is essentially, this is the RAM model I talked about, right? Unit cost to read data from anywhere, okay? But one drawback of RAM is it's volatile, meaning when you lose power or system crash, data in RAM are lost forever. To counter that drawback, several companies have designed this thing called NVRAM. NV stands for non-volatile RAM. So it's just like a RAM, but it's non-volatile. That's kind of like a dream come true, right? It's kind of like behave like a hard drive, but as fast as RAM, meaning there's no difference between sequential and random access. And that sounds like a really cool thing to have, right? So it's yet to be seen what exactly this thing can deliver, but I can tell you one thing for sure, this is not going to go away, even with the introduction of NVRAM, because everything, there's no free lunch. This thing definitely comes with a price tag, for sure. That's for sure. So dollar per byte, if you are us, you only have a few gigabytes or a few hundred bytes to deal with, that's fine. You pay a little bit more, then, fine. But if you're Google and Microsoft, there's the scalability, right? You have petabytes of data, then this dollar amount accumulates to a staggering price that you cannot simply just ignore. And there might be other associated drawbacks or limitations to MMR. Just like SSD, this sounds really nice, but when it comes to random bytes, it becomes really expensive. Okay. Okay, so we understand now. We understand the storage medium. Now let's move on to the next part. So we talk about DSpace Manager. So that's basically the DSpace management part in a database system. So once you understand this different storage media, right? Main memory, SSD, hard drive, what goes into that DSpace Manager? What goes into that DSpace Manager? Well, DSpace Manager will maintain files, allocate and deallocate pages, allocate and deallocate files, which I will explain in a minute. But one thing, before we go into details of that, one thing we need to be aware of is CPU, the processor, only operates data over main memory. Remember I said in my last lecture, we go with this particular abstraction that we ignore the data transfer between main memory and cache for now. Later when we go to main memory database, I will talk about that in details. But for now, in our model, we ignore the data transfer between main memory and cache because CPU actually only operates over data in cache. CPU doesn't even operate over data in main memory. But in our model, we use this simplified abstraction where we argue CPU operate over data in main memory. So, but we know data from database are stored on disk or some secondary storage medium, either disk or SSD. Why? Because those are non-volatile. Memory are volatile. You cannot store your data on some volatile storage medium. This brings up an interesting challenge, which is whenever you try to do something to your database, you cannot operate over data directly from that secondary storage medium, whether it's a disk or SSD. You need to bring those data to main memory first, so that your CPU can operate over that. And this introduced another major component in database kernel is called buffer manager. So buffer manager maintains a buffer and manages this buffer for your DBMS. And the buffer is nothing else but a collection of main memory pages, So this is an illustration of buffer pool, which has, in this case I have 18 main memory pages. I have 18 main memory pages in this buffer pool. It's a fairly small buffer. Typically, you set up your database server with 2 gig or 4 gig or even 8 gig of main memory buffer. Okay, allocated to your DBMS. By allocating, I mean the rest of the OS processes cannot access that space anymore. It's dedicated to your DBMS process. Okay, that's what I mean by allocating memory to database buffer. Okay. Each of this is a page, and in this picture, a black block denotes a buffer pool frame that's occupied. A white block denotes a buffer pool frame that's still available to use for subsequent requests. Your pages of your data from your database are located at this secondary storage media here. Let's say your hard drive. Okay. And what happens is whenever some process, for example, there is an SQL query, comes in and asks for a particular page or a particular set of pages. For example, say let's start from student where student ID equals 18. We can expect that a student record will fit into one page. Okay, so this particular query will translate to retrieving that particular page from the hard drive. the page containing student record equal 18. You follow me? And remember, as I argued in last lecture, the smallest unit in DBMS to operate over is a page. So even if the student record, let's say, is only 10 bytes, you still need to retrieve the whole page. Typical page size for a database is either 4 kilobytes or 8 kilobytes. You still need to read 4 kilobytes or 8 kilobytes, even though that student record only occupies, let's say, 10 or 100 bytes. Because the smallest unit is a page. Even though, in fact, for disk, if you're concerned about a particular disk, the smallest unit is a sector, which I argued again in last lecture. Typical value for sector is 512 bytes. But DBMS has a higher level abstraction, the smallest unit becomes a page rather than a sector. Okay? So whenever I try to read a record, I don't actually just read that record from disk. Never happens. You read the page containing that record. Okay? And the page needs to go to somewhere. Once you have fetched that from hard drive, it goes into your buffer. You follow me? And this brings up an interesting observation, which is, what if there's another query? So let's say I just issue this query called select star from student where student ID equal to 18. And then another guy comes in and says select name from student where where student ID equal to 18. So I want to, the first person want to see all values for that student record. The second person want to only want to see the name field of that student record. The first person obviously have to wait for the database system to fetch the page from disk, place into the buffer, and now you can go to that particular frame, buffer frame. Let's say this is the buffer frame that holds that student record. So I will go into that buffer frame, get the fields out, and I'm done. What about the second person? Well, the second person is a little bit is the lucky guy in this process because he or she doesn't have to wait for the database management system to go and fetch that disk from that page from the hard drive because it's already cached in the buffer. It's already cached in the buffer. So it will be really fast. Once you send the request to the buffer, buffer can return immediately. If the data you are requesting already exists in the buffer frame, in one of the buffer frames. Okay? So the particular data structure, by the way, you guys will be implementing this in your project one. The particular data structure for your buffer frame is the following. You have a frame number, 1, 2, 3, 4, so on and so forth. Right? You have a frame number, page ID. Page ID is the page that currently occupies the buffer frame. This will be now if it's an empty buffer frame. Otherwise, it will be whatever page ID that currently occupies the buffer frame. Pin count and dirty. The first two fields are easy to understand. What are pin count and dirty? Okay. Let me explain the dirty bit first. Then I'll come back to pin count. This dirty field is a single bit. So it's a single bit. It's a flag, true or false. To denote whether this page has been updated since the last time it was brought into the memory buffer. This is critical because if it has not been updated, then when I need to kick this page out of the buffer frame, I don't have to worry about writing this page back to disk because it has not been updated since the last time it was read into buffer from the disk. On the other hand, if some process has updated this buffer frame, this page, since the last time it was read from disk, it was brought into buffer from disk, then I do need to write this back to make sure this change is permanent. Or in other words, is persistent. You can only make the change persistent by writing data back to a non-volatile storage medium, which is your hard drive in this case. You follow me? So that's the purpose of the dirty flag. By default, it obviously is not set. Whenever you update a value in that page, then you set that dirty bit to true. Okay? What about pin count? What about pin count? Pin count denotes how many active processes inside the DBMS are currently using this buffer frame, are currently using this page. And this is critical because if pin count is not equal to 0, whatever value it is, 2 or 3, that means there are some active processes are still using this page, and you cannot kick out this page from the buffer because somebody is still using it. They might come back and make some change to this page. It's kind of locked in to the buffer. That's the purpose of pin count. You can only kick a page out of buffer if pin count equals to 0, meaning there are no active process are currently accessing that page. You follow me? So how do you manage pin count? Yeah, question over there.
So would there be any difference if they're just going to be reading or they potentially be writing to it?
Okay, there is a difference. The difference is it will take some time, take a longer time to update the pin count value if it's a write process versus read. I mean, that's exactly what I try to explain next. When I say a process in a database management system, I use this word because it's too early for us to talk about this, but later on you will know all processes in a database workload are represented by this thing called transaction. A transaction. Okay? So when a transaction tries to read or write one or multiple pages, it will update the pin count accordingly. If it's a read only operation, okay? If it's a read only operation. Typically what happens for a read only operation is you will set the pin count, you will increment the pin count by 1, then you decrement the pin count by 1 after you are done with after you have obtained the content of the page. You follow me? So it increased by 1, then decreased by 1, and this process happens really quickly for read operation. For write operation, somewhat similar. You increase the pin count by 1 as soon as you have brought the page into the buffer, but then you have to do something to figure out what to update, right? That can be expensive. Maybe you are doing some expensive calculation to figure out what's the new value to be written back. Maybe it's some cheap operation, you can do that really quickly. But the point is, it will do that decrement of pin count sometime later. And this period typically is longer than that read operation. You follow me?
What if a process crashes before we...
That is too early, I cannot answer that question now,
Okay.
because we need to understand how do we guarantee the ACID property of transaction. It's just too early to go into that discussion. For now, let's assume the transaction will not crash. Okay, it will execute normally. Okay, all right, that's our assumption for now. And the other thing that's interesting, follow up to the question is, what happens if two transactions try to actively write to the same page? Whose write is going to survive in the end? That requires the concept of locking as well, which we will not be able to discuss at the moment. Okay. All right. So that's kind of the data structure for your buffer frame. That being said, then there's an interesting challenge, which is when you have available frames. This problem is simple, right? You request a page. If it's already in the buffer, you return the frame ID containing that page. If this page is not already in the buffer, you go to disk, fetch that page, find an available frame, place that page into that buffer available frame, and return that frame ID to the process who has requested. What if you have no available frames left? What if you have no available frames left? That's when it becomes challenging, right? What if you have no available frame left? This introduces the concept of buffer replacement policy, which you might have learned from, say, operating system class. The idea is to use some kind of policy to determine which frame to be replaced next. For example, you can use IRU, the least recent used frame. That will be the frame I will replace. Of course, there is a condition. You only replace the frames whose pin counts are 0. Among those, you rank them by who has been least recently accessed. And that's the frame you're going to kick out of the buffer. But you only consider those pin count equal to 0. You follow me? And least recent use sounds like a very intuitive approach. If a frame containing a page that has not been accessed for a long time, then the probability of some request will come back and request that page is fairly low. So I will bet on that and replace that. Right? That's the intuition behind this. But you could be making a terrible mistake if you do this. For example, if you do something called sequential flooding, what happens is, so let's say I have 5 frames in my buffer. Then on my disk, I have 6 pages. And my buffer frame ID is ABCD. Okay? I have a request. My request sequence looks like this. 1, 2, 3, 4. So when you request 1, what happens? You go to the buffer, 1 is not there, you have to go and fetch from disk, place into one of the available frame. Pin count goes to 1 and quickly drop back to 0 because it's a read process. You follow me? And 30-bit is not set, it's read only. 2, 3, so far so good. You play 5 comes. Now the interesting part is when you come to 6, if you're using RRU, what happens? All of these are candidates to be replaced because all of them pin count equal to 0 at this point. So you can replace any one of them. If you're using RRU, which one you should replace? You could replace 1, right? Because that's the least recent use. But if think about I'm the adversary, I'm playing against you. I observe you what you do. Okay, I observe. Okay, you replace 1. So I suspect you are using RRU. So what I will request next is 1. Okay, I will request 1, which is what you just replaced. Too bad for you. You have to pay 1 more random IO to get 1 back into the buffer, which you have just kicked out. And you replace 2. Because that's become now the least recent use. Now I'm the adversary again. I say, okay, all right, I will request 2. And this is worst nightmare for you, right? Because you are always replacing the page I will be requesting next. What's the optimal strategy here? If you know that's what the adversary is going to do, you're going to use MRU. So in other words, instead of, when you request 6, instead of replace 1, you replace 5.
What was the M?
Most recent use. So when you request 1, 2, 3, 4, now they are served without any visit to the hardware. But again, this adversary can observe what you do. If that's what you do, I will not request 1, 2, 3, 4 next. If you replace 5 with 6, I don't request 1, 2, 3, 4 anymore. Who says I have to request 1, 2, 3? I will request 5, 4, 3, 2, 1. Now, if you use MRU, again, you end up replacing the very same page that will be requested next. And this is what we call an online game between the two, right? So it's a very tricky game. So how do you possibly win this game? How can you win this game? Okay. This brings up this concept called competitive ratio for our algorithms. Competitive ratio for our algorithms. Competitive ratio for our algorithm. What that says is, first of all, you have to accept the fact there is no optimal online algorithms. You cannot just design this. You cannot hope for the optimal online algorithm. The reason is the sequence is a dynamic sequence. the adversary can always observe what you're doing and come up with a design that defects your algorithm. So there's no such notion of optimal quote-unquote online algorithms. However, you can quantify the behavior of your algorithm by comparing the cost of your online algorithm versus the offline optimal. Offline optimal meaning you ask the adversary to place out his or her request sequence ahead of time. Whether it's 10,000 requests or 1 million requests, I don't care. But tell me your request sequence ahead of time. And give a value k, which is the number of buffer frame I can have. What is my optimal strategy to replace frame in buffer? So basically, you are given the input ahead of time. In other words, you cannot know the future. That's kind of the best you can do, right? And this cost can be high, can be low, right? Depending on the setup, right? For example, if you only have one buffer frame, I gave you 10,000 distinct requests. Even God cannot do nothing, right? You have to replace every single time, period. But on that hand, if it's 1 million requests to the same page, even a dummy can do this really well. Just whatever algorithm will work out the same, which is no replacement because it's always to the same page. So obviously there is trade-off here. I don't have time to talk about these details. I will continue from here next lecture, but using the rest 1 minute, I'm going to show you the simple DB really quick, and you can start reading this Java doc and form your team. Okay? So you will be given this code later on, but what simple DB looks like is this. So this is how I start SimpleDB, and I have a particular database I have set up, which is the IMDb database, the movie database, right? Okay. And then you can do things like, and I will execute this query. Okay. And what this looks like. Okay, so that's this query. Let me run another query. And this actually shows you the query plan for that particular query. Right? Query plan for that particular query. So you go of this master. At the end of the day, you can claim you know database system where you can build this system and your system can run and execute query and output query plan, different query plans. And okay, this shows you the query plan. Right? So by the way, if I show this query plan quickly, as you notice, it used relational algebra, right? Kind of notation, projection, and so on and so forth. Okay. And what this table looks like, by the way, I'll show you real quick. This is the schema of that table. And when you load the database with this schema, what happens is it will convert this schema into something called catalog, which I don't have time to cover today. Continue on Tuesday. But the data is converted to the .bat file. Initially, they are in this txt format, but then they are converted to this SimpleDB.bat file. And you will be start working on this next week. Okay? But start reading that, please start reading that Java doc. Okay? Alright, see you. So how many people in your team? Well, I'm still leaning towards just 2. Okay? So let's just do 2% here. Because having 3-person team, I'm worried that one person will always get the free ride. So let's just do 2.